Hello everybody, Gadget Boy here, and we're here with the final of my three, I don't need that, the final of my three Christmas mystery kits that I was given. Only this one isn't so much of a mystery. This one was labeled Melody Voice. And on inspection of the tracks on the back and the way it's arranged and the components that are involved, hey, this one actually tells me 3 to 5 volts, so I know how much to give it. It looks like it's going to be some kind of view meter, because we've got the LEDs all lined up in parallel, which actually means they're not going to light sequentially. It's just going to be a bar of light that pulses in reaction to the sound coming from the mic. We've got 2 transistors arranged in a Darlington pair, being used for their amplification properties. Now, we've talked about transistors before being used as doors, but the other application that you can use a transistor for is as an amplifier, because, come on pen, work, there we go. When you have a transistor here, we'll just use a standard NPN transistor. Oops, come back here faster. The current flowing from the base to the emitter is based on the amount of current, or from the collector to the emitter, is based on the current coming in from the base. And that is actually amplified. Like, each transistor has a property called beta, and the beta is the amount by which the current coming into the base is amplified through the collector and the emitter. And that's a little thing that looks like this, a little B with a dangly bit coming off of it. And let's say, for instance, that this transistor has a beta of 100. That means that whatever current is being applied to the base of the transistor is multiplied by 100 from the collector to the emitter. So if we have, say, 100 milliamps coming in to the base, and that's actually a lot of current to put into the base of a transistor, we're going to have 1,000 milliamps going from the collector to the emitter, or 1 amp. That would require a much larger transistor than these. These generally deal in microamps, or microamps of current being multiplied, then across the collector and the emitter. Now, on this one, sorry, I had something stuck in my throat, we're going to be working with something called a Darlington pair, which is when you take one transistor, that's looking more like a MOSFET the way I drew it, but that's a transistor. You take one transistor, and you take the emitter of that transistor and connect it to the base of another transistor. And by doing that, you actually multiply the increase in the current flow. So in this case, we're going to be using the Darlington pair to amplify the current coming out of the mic, because the microphone is probably generating nanoamps. So let's say this one has a beta of 100, and this one has a beta of 100. That makes the total beta of that Darlington pair, because you've got the microphone current coming into the base of the first one, which is multiplying the current going from the collector to the emitter, into the base of the second transistor, which multiplies the current coming through the collector and the emitter. Probably in this case it's just going to be common like that. And then that multiplies again through the second transistor, so we're going to have a total beta of 10,000. So the tiny amount of current being generated by the microphone is being amplified 10,000 times to control the amount of current going through the LEDs. And then that current control will make the LEDs pulse in brightness based on how much current is going into them. So that's just a quick primer on Darlington pairs. I need to do a proper video on transistors at some point explaining their the exact way they work. This doesn't have a lot of components, so I'm probably not going to time-lapse it. We're just going to slap it together. Let's see, we've got a 1 megohm resistor, which is going to be 1 million ohms. So we need a 1, a 0, and then six zeros. So we're going to need black, brown, violet, I believe. No, sorry, black, brown, green, which is this one right here. I had one too many zeros in my brain there. So that's the 1 megohm resistor. So we'll just quick solder that one on right here. Oh, I got my solder all tangled up in my solder dispenser spool. Come on, you. There we go. So there's that. Where's my diagonal cutters? There we go. So there's our 1 megohm, and then we need a 4.7 k ohm resistor, which is going to be yellow, violet, orange. Or yellow, violet. Oh, sorry, 4.7K. That's yellow, violet, red, not yellow, violet, orange. Yellow, violet, orange would be 47K. So there's our yellow, violet, red. And we'll put that in the 4.7K ohm resistor spot there. One thing I've noticed about these mystery kits is that the boards really do not like to take solder very well. It's a little frustrating. So I've been wasting a lot of solder on these. Alright, the next one, well, it's going to be the last one remaining, is the 10K ohm resistor, which is going to be brown, black, red. Or 10K. Brown, black, orange. I got my reds and my oranges confused on both of my resistors here. This is, brown, black, red would be 1K, not 10K. Come on, take the solder. Like I said, it's been a little difficult getting these pads to take solder. They look nice enough, but they just haven't been soaking it up. It's a little... I think I know why. It's the pads are only on the back, and they didn't run any solder up into the holes of the PCB here, so the solder doesn't really like to wick in against the leads. Anyway, so let's see. The next component we should put on, I think we'll go with no, we'll do the transistors towards the end. So let's do the capacitors first. So we've got a 1 micro and a 47 micro capacitor. This is the 47 micro, so it's going to go over here, with the long lead, which is the positive lead, going into the part that's marked as positive. There we go. Make sure that it's nice and flush, which has no purpose other than cosmetic, but I like it to be pretty anyway. So we'll quickly these so difficult to solder? Oops. Oh, that's good enough. Alright, we'll just crop those leads off. We're going to move on to the next capacitor, which is the 1 micro, which is this tiny little thing here. Again, the positive lead is the long one, going into the positive, the whole marked positive. It's holding itself in rather nicely. Trying to iron down a good soldering technique for these. I'm just not having a good luck getting these pads to take solder nicely. But that's alright. It doesn't have to look good, it just has to make a solid connection. So this is the person who's super OCD and likes to make his components line up neatly and resistor color codes to all be pointing in the same direction. And wow, that just went way across the room. Wow. Gotta be careful when cropping off the leads, because they'll pop off and go sailing far, far away. Not like the Enya song. Oops. Come back here. Probably should have done this one earlier on in the process here. This is going to be very challenging to solder on now that the capacitor is in the way. Brilliant job, Chris. So we'll just kind of messily splodge a little bit of solder on there to give us an initial anchor point, and then we'll clean it up now that it's actually holding itself in. There we go. Ow! He says as he singes himself. Crop off the little bit of extra on that one. Nice. And then I think we'll do the microphone next. I haven't marked polarity on this, but it's kind of positional. The leads are coming out of one side there, so if I tried to plug it in the other direction, it wouldn't fit onto the board really well, so I'm assuming that's going to go like that. I don't even know if these little electret microphones have a polarity. I'm reasonably certain they would. So we'll quick solder that on. We can get the pads to, oops. We can get the pads to actually take some solder. There we go. I got way too much solder on that now. Just tap the extra solder off of the iron there. And then solder the other lead of the microphone on. There we go. And crop the extra lead off. Alright. And we just need to throw the transistors on. Again, they've got kind of a physical